So, in the last lecture we had seen how the wave propagates when there is a disturbance in the flow. So, if I have a moving projectile or any bluff body that is moving in the air, this is going to disturb the flow. So, the projectile or the body is going to push the fluid outside the surface, which is going to propagate as a pressure wave. The propagation of the pressure wave is what we have seen as sound wave propagation, and we have seen how the wave propagates when the fluid is incompressible, where the pressure waves are very small. You have a symmetric concentric circles which we had shown to be the propagation of the wave. In subsonic flow you have wave front that is moving ahead of the body, and in a sonic case where the Mach number is 1, we had seen the pressure wave as well as the projectile reaches any given location at the same time. So, there is no information that is given to the measurement point ahead of the projectile reaching that point. So, we will discuss something more on the supersonic case. So, I will try to redraw whatever we had drawn in the other lecture. So, for the discussion today is on Mach wave. So, we have assumed the disturbance is created by a point source. So, the point source is moving with a velocity v, and the sound velocity is, sound speed is a, and we take a snapshot at t equals 3 seconds. Okay. Now, we try to find what is the evolution of these sound waves that is generated few seconds earlier to the snapshot point. So, the distance the wave travelled in 1 second is a, in 2 seconds is 2a, in 3 seconds is 3a. So, we will see what happens to and the 4th second is so the wave that is the wave generated 1 second earlier would have travelled a distance, and the wave generated 2 seconds earlier would have travelled 2a distance, and the wave generated 3 seconds earlier would have travelled 3a. Okay. So, we will see how this has been evolved, how we have arrived at something called the Mach count in the last class. So, I have a point here, snapshot at 3, and velocity is 2a. Okay. If that is 2a, the velocity the wave that has generated 3 seconds earlier would have reached 3a distance. The wave that has generated 3 seconds earlier is 3a distance, and the location of the wave after 1 more second is 2a. So, we have 2a, this source has moved a distance of 2a. So, this is 2a, this is at t equals 0, this is at t equals 1. Okay. So, this is the location where the source would produce a wave which is 2 seconds earlier than the snapshot point. Okay. So, the wave that is generated 2 seconds earlier would have travelled 2a distance. Okay. And in the next 1 second the source would have moved another 2a distance, which is somewhere here, and this is at t equals 2, which is 1 second earlier than our snapshot point. So, that would have travelled a distance of a. So, the wave that is generated 1 second earlier would have travelled a distance a. So, that is this. Okay. And in the next 1 second the source would have moved a distance 2a again. Okay. So, that is at t equals 3. So, the source is moving along this line. Okay. So, the wave that is generated at t equals 3, that is also our snapshot point, will stay there at the source itself. It doesn't move out, because that is exactly the point in which we are taking the snapshot. Okay. So, we have infinite waves that is generated in between, and we are considering only these 3 at present. So, the source is much ahead of your wave. We have also drawn the tangent of all those waves that is generated, and we obtained something called a Mach cone. Okay. So, at this tangent, so whatever wave that is generated in between, the infinite wave that is generated in between would come and hit this particular cone. So, there are infinite waves that is generated as you move from t equals 1 to t equals 3. So, this particular location or the edge of this cone is the collection of all these waves. Okay. So, this edge of this cone is typically called as your Mach wave. And if you look at this geometry, this is 2a distance in 1 second, so last 2 points, and the radius of the circle is a, and this 2a is your v. So, I redraw that. This is at t equals 2, this is at t equals 3, this distance is v, which is equals to a, and it touches the Mach cone at a distance a. Okay. And if I call this angle as mu, then I can write my sin mu as 1 by m, or I will write this as a by v or 1 by m. So, if I have a projectile that is moving with some Mach number, I would have a cone that is generated like this, which is the collection of all the waves that is coming and hitting. We have also seen that this inside the cone is the so called zone of action, outside the cone is zone of silence, meaning any point here would not know about the approaching projectile. The point will know about or hear about the projectile after the projectile has passed, only when the point is inside the Mach cone, the point would measure something or point would hear something. So, this edge where you call it as Mach cone is actually the collection of all this. So, if I have a bullet that is passing, a bullet that is moving in the air at supersonic speed, this would generate a cone like this, where outside cone I have silence, zone of silence, and inside I have zone of action, and this edge of the cone is where all this wave might have coalesced. Okay. So, if a person standing here or a measuring probe that is kept here, okay, will pick some signal only when this goes into this. Okay. If I assume that there is no movement here, if the signal here is 0, this probe will pick some signal only when this wave moves in here, and this the signal would be maximum when it crosses the Mach cone, because that is the collection of all your waves. So, when it reaches somewhere here, so when the projectile moves here, this is inside the Mach cone, and hence they will hear or get the change in pressure at this particular point. So, there are three things to understand. One, the projectile moves ahead of your pressure wave, or the projectile moves, the projectile velocity is larger than your velocity of sound. So, the pressure differences will not be felt ahead of your body. That is point 1. Point 2 is that outside the cone, it is zone of silent. There you will not know about the upcoming projectile till you are inside the cone. Okay. Third, the signal or the effect of pressure variation would be maximum at the edge of the cone, because that is where all your signals coalesce, and the edge is the so called Mach wave. At the Mach wave you will have the maximum variation. Okay. So, that is essentially what we need to talk about the Mach wave. Now, that brings in some interesting phenomena which we will discuss in the form of few problems. Question I have is, a gas with molar mass 44 and gamma equals 1 point, gamma equals 1.3 is at temperature minus 30 degrees Celsius and velocity 500 meters per second. Find your Mach number, which is quite straightforward, and once you have the Mach number, you can find the cone angle, which is also called as your Mach angle. Okay. So, this is your Mach angle. So, the question is straightforward. So, how do you find the velocity of sound? Velocity of sound is gamma r t, gamma into r bar by mm into t. So, this is 1.3 into 8314 divided by 44 into t is minus 300. So, that is 273 minus minus 30. 273 minus 30. This is 253.5 meters per second. So, that is the velocity at which the gases, the velocity of sound at this particular situation. The state is t equals minus 30 and the velocity is 500 meters per second. At that state you have the velocity of sound to be 253 meters per second. If that is the case, what is the Mach number? Mach number is V by A, which is 500 meters per second divided by 253.5 meters per second, which is approximately 2. Approximately 2. If that is the case, your mu is, sin mu is 1 by 2. So, your mu is okay. So, this is approximately 2. So, this would be approximately 2. So, it essentially means, so there is no projectile here, but we have defined a Mach angle associated with it. So, I have a gas that is flowing at minus 30 degrees Celsius at a velocity 500 meters per second. Okay. The associated with this, there is a sound velocity, because we have defined the sound velocity and there is a velocity of the gas that is defined already or given to you already, there is a Mach number. So, with every Mach number you can define a Mach angle. So, even though there is there are no projectiles, we have defined a Mach angle, because all these particles, all these walls of the tube would give you a pressure variation, because it is coming and hitting. So, this would change the pressure. There is a pressure gradient and that pressure wave is the sound velocity. So, compared to that sound velocity, there is a Mach angle. So, for everywhere there is a Mach angle. Okay. So, it is always there, even though there is no projectile. So, the impression that you need a projectile to have a Mach angle is wrong. It is just a phenomena that is going to be there in the supersonic flow. Fine. Now, we will do another questions related to this. Travels 20 kilometer before one could hear. If the cruise altitude is 10 kilometers, what is the velocity at which aircraft? Okay. So, an aircraft flies and it travels 20 kilometer before I could hear. So, what is the velocity of the aircraft? So, I am standing here, aircraft is flown 20 kilometers past me, Okay. At this point I could hear when the aircraft has flown 20 kilometers after me, I could hear the sound. Okay. So, the Mach count that is generated has just reached me. So, this is my Mach count. So, the Mach count just reached me when it is 20 kilometers. So, it is the vortex should be here. Okay, this is my 20 kilometers. I will redraw this here. This is my aircraft. So, aircraft has travelled 20 kilometers before I could hear. So, the height at which the aircraft flies is 10 kilometers. So, what is the velocity of the aircraft? First, let us find the velocity of sound. Velocity of sound is gamma r t. Let us put 1.4 into 287, t is 288 minus 0.0065 into the altitude. Altitude is 10 kilometers, 10 into 10 power 3. So, we have used the temperature to be of the form this 288 minus 0.0065 multiplied by the altitude. Okay. So, the temperature here is different from what you have at sea level. This is an example which you have seen in the earlier lecture. So, use that relation to find the temperature and get your velocity of sound. This is 299.3 meters per second. So, if this is the velocity of sound, now I can find this angle mu, which is this angle mu. So, I know tan mu is opposite side by hypotenuse, opposite side by adjacent side, which is 10 by 20. Mu is mu. From there, sin mu is 1 by m, 26.56 degree and 0.447, and m is the inverse of that, it is around 2.23. Okay. So, now we have the velocity of sound, we have the Mach angle. From the Mach angle you can find the Mach number, and hence the velocity of aircraft is 2.23 in V by 2993 meters per second. So, V is 669.2 meters per second. So, this aircraft is moving at a velocity of 669.2 meters per second. at a height of 10 kilometer. So likewise you can find if you know the time difference between these 2 points, you can also find the velocity of aircraft. Okay. So the aim of this exercise is to understand Mach wave and Mach angle, how it is useful in computing the quantities that which I have just shown, and the presence of a projectile is not necessary to have a Mach angle. If there is a supersonic flow, you would definitely have a Mach angle. So in a supersonic wind tunnel, there are Mach angles at all points. So your if I have a cross section, if this is m greater than 1, there will be Mach angles all the ways. Everywhere there will be Mach angles. All those points would create a phenomena that which we had just seen. Okay. But in this case it is a stagnant air and there is a projectile that is coming. So this is creating the supersonic wave, and hence you have one Mach wave. Right. So so we had seen how the propagation of pressure wave generates new phenomena in a compressible flow, where you have pressure variations which is given as the velocity of your velocity of sound, which generates the phenomena of Mach waves and Mach angles. Okay. Thank you.